Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to review the unit on graphs, equations, and applications of sine functions. In this unit, we learned all sorts of things about sine functions, and hopefully by now you're able to demonstrate to anybody that you understand a periodic relationship. You also understand these sine functions, and you're able to make connections between the numbers, the graph, and the actual algebraic equation that would represent a sine function. Hopefully, you're also able by now to look at a situation and identify whether that situation represents a sine function, and then solve problems that involve that situation, especially ones that come out of the real world situations. At the beginning of this unit, we noticed that there are many situations in life that occur cyclically. And this sometimes happens when an object is rotating. Very often, there's a cycle, and literally, we use the word cycle for the front wheel of a bicycle or a back wheel. I guess any wheel doesn't really matter. It also happens when we look at planets orbiting a star. All of those are objects rotating. Whenever that happens, that creates a cycle. If we take any point and we start to have it rotate around or orbit around a center point, well, the path that that point makes as it's orbiting creates a circle, just like that. And in this unit, what we learned is if we take that point and we connect it with a line to the center of the circle, and we look at that line and say, hey, that's the radius of the circle, we can actually make it the hypotenuse of a right triangle. And the reason we would do that is because then we can measure the sort of vertical distance and the horizontal distance because those are perpendicular. That would make a 90-degree angle right over there. And that's the connection between between circles and triangles. When an object is rotating, we can use the right triangle that is formed to find out all sorts of things about that point that's rotating around or orbiting around the edge of that circle. And in this unit, we learned how that relates to the function sine x, the sine function. The function f of x equals sine x tells us what is the vertical distance of that point from the center, just the vertical distance, not the radius, not the actual distance, but just if there was a horizontal line going through the center of the circle, what would be the distance between that line and the point? We can find that by using the function sine x, and where x is the amount of degrees that the point has rotated from its original starting position, which is the right side of the circle right here. Because this point will complete rotating around and around the circle, and every 360-degree rotation will complete the circle and then start the cycle again, that's what makes the function sine x periodic. So this height changes as the degrees increase, but after 360 degrees, that's a full rotation. And the graph of that just looks like this. So as it rotates this way, we notice the distance, the y value, or the distance of that vertical line, it starts increasing until it increases to its maximum of 1 unit, where the 1 unit is the radius. And then it starts to decrease as the point gets closer and closer to that horizontal axis, until it reaches back to 0. And then as it starts to go below, we still measure that distance, but now we express it using a negative number until that point has rotated all the way down here, and then this distance would be -1. And then the point will continue on, getting closer and closer back to 0, and that is one full period. This is the graph of the function sine x. It looks like a wave, and that wave has a period of 360 degrees. So that means a full rotation restarts this sine wave. It also has a couple of other properties called the midline at y equals 0. The equation of the axis is another way to describe that midline. It has an amplitude, and amplitude is another property which we talked about, of 1. Its domain is any real number because you can rotate a real number of degrees, but the range is limited at the bottom and the top. The minimum is -1, the maximum is 1. And if you want to sketch out a sine function, these are the 5 key points to remember. The x values start at 0 and they just go up by 90 degrees, 0, 90, 180, 270, 360. And the y values go 0, 1, 0, negative 1, 0. So this is the midline, up to the maximum, down to the midline, down to the minimum, and then back up to the midline. Now that we know what that function kind of looks like, let's take a look at each of these properties in a little bit more detail. So first up is the period. That right there would be one complete pattern that starts to repeat itself. And that happens when the change in x is 360 degrees. So the period is the interval of x that completes one cycle. Next up, we have the midline, which would be right over here. The midline is a horizontal line that goes in through the vertical middle of a function. So basically, for measuring the function vertically, the middle of it, halfway between the maximum and the minimum, that right there is where we put the midline. The amplitude is the distance from the midline to the maximum or from the midline to the minimum. We always express that positively. And in this case, it has an amplitude of 1. Finally, the minimum is -1 and the maximum is +1. And that's how we get the range of the function. In a real world situation, the places that we would see sine graphs are usually with rotation. And all of the various properties of the rotation actually connect to the sine wave. The radius of the wheel tells us the amplitude of the graph. The rotation speed will determine the period. And the height of the axle, which is at the center of the wheel, that is also going to be the same as the height of the midline or the height of the axis. Finally, one thing to keep in mind is sine of x usually starts on the midline and it increases from there. So the starting point of the rotation, if it doesn't start on the right side of the circle, that will actually determine where the graph actually starts or what the initial value is. And we saw all of that happen in this nice summary table. So if you have a point rotating counterclockwise from a starting position on the right side of the circle, if that point rotates 1 degree per second, you can very easily find the total angle of rotation by taking, well, the number of seconds that have rotated. That's how many degrees it will have rotated. And to find the y value, to find the height of the point above the middle of the circle, you can just do sine of x, where x is the angle of rotation. But if we make that circle bigger, now the radius is 2, well now once we find the coordinate, the y value, we have to multiply that by 2 to find the actual y value, because now the point is further from the x-axis, as you can see when you compare these two. If we make the rotation happen faster, well, that would change the angle of rotation dependent on time. So after x seconds, the angle of rotation will be 3 times x if it was 3 degrees every second. If we move the center of the circle up or down, well, that means that we have to, once we find the y value, which is the distance from the center of the circle, well, the center of the circle is a certain number of units, in this case 2, above the x-axis. So if we want to find the y value, we have to find the height here and then add 2 to it afterwards. And finally, if the point starts by rotating not at the on the right side of the circle, but somewhere else, well, that would change the angle of rotation, not by multiplying it, but instead by adding some number. In this example, because it started here, that was an initial rotation of 90 degrees. So if 10 seconds had passed, 1 degree per second, that's 10 degrees in total. You would have to add that to the initial 90 to find out it would be a total rotation of 100. This is what the graphs of all of these looks like. So this would be just the graph sine x. But when the radius gets bigger, we notice that the amplitude is affected by that. The graph gets vertically stretched. When we increase the rotation speed, we decrease the size of the period. So it actually rotates much faster, so it can complete one cycle in even less time. If we change the height of the circle, which means we're adding 2 after the sine function, that would change the entire graph to be translated upwards. And finally, if we start the rotation somewhere else, well, then the initial value will not be 0 like it is in all of these cases, but it will actually be something else depending on what the y value of that point is at the start. Notice that this is the normal graph of sine x, but each of these was transformed in some way. This was vertically stretched, horizontally compressed, translated up, and translated to the left. Looking at those a little bit more in detail, we learned that there is a function template which we can use, which looks like this, where a, k, c, and d are specific numbers that will change what the graph of sine x looks like. If you change a, that causes a vertical stretch or compression. Or if it's negative, it causes a reflection. So imagine this is a linear scale where you see a. Normally, what is sine being multiplied by in order to not change its value? That would be 1. So if it's 1, it's not being stretched or compressed, and it's not being reflected. But if we increase the value of a to more than 1, that would create a vertical stretch, as we'll see in just a second. Right now, you can see that's being stretched, and that changes the amplitude as well as the maximum and the minimum. And because the range depends on those two, it of course affects the range as well. But notice that the period has not gotten smaller or bigger. The midline is still at y equals 0. Next up, let's take a look at k. Well, changing k actually horizontally stretches or compresses the function, but we say it does so by a factor of whatever the reciprocal of k is. So if k is 2, the reciprocal would be 1 over 2. It also, because we can see that happening right here, it changes the size of the period. The new period will be 360 divided by whatever the positive value of k is. It does not change, however, the amplitude, which you can see is still just 1, the maximum, the minimum, the range, which depends on the maximum and minimum, the midline, which we see right here, or even the domain. The domain will always be x is any real number. When we change d, we notice the function being moved left and right. Now, this doesn't change very much about the function at all, but it does change the starting point. Note that it's kind of easy to miss this, but when you see x minus 45, d is not negative 45, it's positive. And that's because the template has the expression x minus d. So you actually have to switch the sign when you're trying to figure out what d actually is. Finally, we have c, and as you can see, the function is being translated up or down. When c is positive, it goes up. When c is negative, it goes down. And that, of course, affects the midline, the maximum, the minimum, and the range. It does not, as you can see here, change the amplitude. It doesn't even change the size of the period. And once we know all about transformations, we can actually use those to sketch a graph of a sinusoidal function. So for this function, y equals c is the midline. The amplitude is the positive or the absolute value of a. And if we start at c and we go up and down by a, up by a and down, that would tell you exactly where the minimum and the maximum of the function are, which tells you the range. The period can be is affected by k, so the period is always 360 divided by the absolute value of k, whatever the positive number is. And the function normally it starts at 0, but now it's been moved left or right by d, so it actually starts at whatever the d value is, and it ends 1 period later. So we just take that d value and we add p, and we'd find the end point of one single period. Now, if we have all of this information, we can just sketch a sinusoidal function by first sketching a box using the starting and end points, the minimum and the maximum, and then just plot the 5 key points for the function. And the only thing to keep in mind here is if a is negative, the function will be upside down. Finally, we learned that sinusoidal data exists not only from rotating objects, but also from any oscillating motion, anything going back and front, such as a swinging pendulum or a ride. In real life, if we notice that data might be acting sinusoidally, if we actually collect that and graph that data, we can create an equation that matches that graph. And we can use that equation or even just the graph itself to think about questions that we could ask or even questions that we can answer about the data. The only thing to keep in mind is because this is a real world situation, the domain and range will be affected by that. So you have to keep in mind that when you're expressing the domain of the function, it's not just reflecting the function sine x, but actually the real world. And that's that for this unit. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.